All right, good morning, chemists. I'm glad you are here. Um, Most people have looked at their midterm and, probably were not happy with what they saw. And that's very understandable. As I already indicated, the first midterm typically is somewhat disappointing in this course. Part of it has to do with the fact that this is very new to most people. It's really hard to relate this to the rest of chemistry and some new concepts, some new ways to think about things. And that's, it's difficult to really put your finger on it. So it's not unusual to get a grade back that is a little bit disappointing. I would say don't give up, okay? Don't be demoralized. You will see that all of these things will come together and we'll apply it to some molecular systems, and you realize that many of these things that we have been talking about will be very helpful as you move along. So don't give up, folks, please. I will be talking about the midterm in my office hour this afternoon from 1 to 2. I'll be going through all questions on the midterm and explain a little bit about ways to think about these questions and how you could have solved it. I posted already the key in effect on the website, so you may have seen that one as well. But I think it's useful to walk through those answers anyway, so people can ask questions about, hey, I don't really get it. Why is the answer like this and not like that? So that is a good time to ask such questions. I'll be walking through them one by one. Another thing that has come to our attention is that someone, has taken the time to take screenshots of the midterm and post them on check.com, which is a website that features questions, and then experts will be answering those questions. This happened during the midterm. Evidently, this is not allowed, folks. We can't have that, right? Because if answers are being posted during the exam, that means that students who have a check.com account will take advantage of that over other students. So that means we have a very unfair performance distribution on the exam. So this is something that we take quite seriously. As you noticed, I did not activate the responders monitor this time. The reason for that is because there were some problems in the past with activating the monitor. Some people had issues with that. And so we decided not to do it this time, but it looks like we just have to do it next time around, because people are, just basically abusing the situation. So we're launching an investigation. We're looking at, whether answers on check.com are posted during the exam. And if that is the case, we don't know yet. But if that is the case, then what we will do is we have to null the entire exam. So basically, the midterm will not be part of the cumulative grade. We have to redistribute the weighting factors and so forth. So it's a lot of extra work, but we'll see. So we work with check.com to figure some things out, and maybe nothing will change, but maybe something will change. You'll hear from us next week. This investigation is ongoing. So I'm a little disappointed, folks. I put a lot of time and effort in this course. Every year we make new exams. It's a lot of work to make good exams that are balanced, that are fair, and to see them posted online is just is not good, because it's a lot of extra work for us. Okay, so we like to compare performance from year to year between different classes, and if we have different exams, it's difficult to compare performances, right? So we would like to recycle some of these exams, but if they're posted, we cannot do it. So it really messes up our teaching organization, and it's just not fun. So next time, please, even though it's very tempting to post questions and ask somebody else for help to solve those questions, it really is not the purpose of learning about new material. Quantum mechanics is a lot of fun. It's not, like I said on Monday, it's not about only scoring 100%. It's not about it. It's just about learning something new, and it's fun. Okay, so if you just play by the rules, then you actually maintain that fun factor. If you don't play by the rules, then everything becomes stressful and agonizing. So that's my 2 cents on that topic. You will hear more about it as we move along. All right, let me check the chat. There's a lot of chat going on here. All right, we don't know. We don't know who posted. We have some suspicions, but we don't know. The point posting on check.com is not a violation of anything in principle. Okay, it's a website that is doing their best not to promote cheating, of course. I mean, they're very serious about this, right? And there's a chance that none of this has affected anything. But if answers were posted during the exam, then it has. And that's what we're trying to figure out. So it's not so much about the person who did it. It's more about whether or not answers were posted during the exam. That is the issue here that we're trying to find out. All right, so. Okay. Any questions, folks, about this? I don't have any clear answers. We only have answers maybe next week, but that's the situation right now. Okay. All right, then I'll just move along. We have some stuff to cover, folks. Yeah, let's see. Is there a chance that a person posted the answer solely to nullify the exam's grades and hurt everyone? I don't know. We don't know that. We don't know the intentions of the person. So it's unfortunate, but this is what it is. We'll just deal with it accordingly. All right. Let it not kind of like dampen the fun that I was trying to build up here. So let's just continue, and we'll deal with it as we go. All right. So I'm going to talk about something that we have already partially covered, and I'm going to basically tie it into something very interesting. That you will see at the very end of this lecture will look very familiar, but you didn't know that it was coming from this angle, literally from this angle. Okay, so here we see again a particle that's moving on a ring. Okay, we have talked about it now several times, and I'm going to approach this again from the perspective of angular momentum. Okay, so I'm going to repeat some of the things that we already know, but that's okay. We have to rub it in several times before it really sinks in. And then we're going to connect this to something really general, and then make it really specific again at the very end. Okay, so here's a particle on the ring. The ring has a distance of r. That is actually a vector. Okay, so the vector r, it's in the Cartesian coordinates here. So I can have the Cartesian directions I, j, and k. All right, and then of course x, y, and z are the distances along those directions. All right, so r is a constant, but of course its direction will change because it's going to spin around. It's going to spin around because the particle has linear momentum, that is p, that is tangential to r. Okay, so wherever r is pointing to, then 90 degree relative to that is what p, the direction of p is. Okay, so p is also a vector, therefore. Okay, it's also, of course, can be described as a Cartesian vector that has the directions I, j, and k, and that means it has the components along x, y, and z. Those are the components of the momentum. All right, so we have two vectors, r and p, that define this motion. Now, we already said that there's something called angular momentum. Okay, if the particle is spinning around here in the xy plane, then there is an angular momentum that I can calculate. That is the vector product of r times p. All right, so we know that this is fulfilling the so-called right-hand rule. This is what we showed last time as well. So the vector L is basically a times b, a vector product of b, where a is the radius and b is the momentum. Okay, that's going to be L. L is going to be pointing up, therefore, and we can compute it. We can compute this L. This is all classical mechanics. There's nothing quantum mechanics about this. We just do the vector product. Okay, so this is how you can calculate the vector product. And this time, I'm going to write out the entire thing. Okay, the entire thing. And that's this one, right here below it. So I'm going to write out the components along the direction I, which is along the x-axis, right? So that is y times pz minus z times py. That's the first part, the first component, this one here. And I'm going to do the same thing along j and k, right? So along j, I have k times pz, sorry, x times pz, and then minus z times px with a negative sign in front of it. So I get the following, pzx minus x pz. And then finally, direction k, I have x times py minus y times px. That's this last term right here. So I have three components of angular momentum. One is directed along x, one along y, and one along z. So I can write this whole thing in this fashion. So I have a component Lx, the angular momentum along Lx, along the x-axis, Ly, the momentum along y, indeed, and then the momentum along z, Lz. So what I'm seeing here is that I have basically three components. Previously, we only talked about this one right here. Okay? So this one is the angular momentum that's directed along the z-axis. And that is what you get when you have, of course, a motion of the particle in the plane. Okay? So if it moves in the xy plane, then the component is along the z-axis. But the particle is not restricted necessarily to move only in the xy plane, because as we saw for the particle on a sphere, it can move anywhere along the sphere, really, keeping r constant. It doesn't have to be in the xy plane. It can be in different planes. And that is basically why we also have an Lx and an Ly component. So in principle, I can do the following. So let's say I have here, the ring motion. So let's say, it moves in this direction. That means there is a Lz that points this way. This is Lz, okay, along the z-axis. But what if I have now a particle that is spinning around in the zy plane? So let's say it moves in this direction, okay? That means that I have an angular momentum that's directed along x. That is going to be Lx, right? Also, I can also move along this plane here, this black line right here. If I move in that black line, along the black line in this direction, that means I move in the zx plane, then I have an angular momentum that points along the y direction. So that's Ly. So that's basically what it means, right? That's what it means. So here are the different components, Lx, Ly, Lz, okay, that I can compute purely classically. Okay, so again, there's nothing like quantum mechanics about this. This is just pure classical mechanics of basically angular motion on a sphere. The angular motion can be characterized by angular momentum. And I can do that because I can decompose angular momentum in its respective components. And this is what these components mean. It's indicated by this illustration here at the left bottom of the slide. Okay, so the z components of angular momentum, now I'm going to put a little hat because now I'm going to talk about something quantum mechanics. Okay, so Lz with the hat is the operator. That means this is what we did last time, put little hats on the respective operators, on the respective components of the angular momentum. And we computed last time what that's going to look like if I do this in polar coordinates, because what I got is h bar over I d phi, where phi, of course, is the angle that the vector r makes in the xy plane. Right? So that's what we computed last time. So we have actually a functional form of Lz. Operator Lz looks like this expression right here. Okay? This is nothing new, of course. This is something we have seen before. Now, I'm also interested in the magnitude of angular momentum, because what I say here on top is the z component. So this is a projection of the angular momentum. I can also talk about the magnitude of angular momentum. And I'll put this into a graph 2 slides from now. You will see this. You'll see exactly what that means. The difference between a projection onto one of the axes, in this case the z component, and the actual magnitude of angular momentum. So I can compute the magnitude of angular momentum. Again, this is purely classical. So again, I'm not using anything quantum mechanics here. Just L times L, the vector L times itself, okay, will give me the magnitude squared of the angular momentum. So I can compute that. That's what I'm going to do. Classically, once again, between parentheses, I have the expression for angular momentum, the vector for angular momentum, which has, of course, components, Lx, Ly, Lz. I'm going to square the whole thing and see what works. All right. So what happens is the following. I get, of course, each component times itself. So I get Lx squared, Ly squared, Lz squared. And then I get the cross products. Okay, so I have to, of course, take the cross products between each and every one. And so I get twice Lx Ly, twice Lx Lz, and twice Ly Lz. The only thing I do is just evaluate this quadratic expression above. That's it. But the good thing, of course, is that these two vectors, I and j, are orthogonal. Okay, and that means that their product is going to be 0. They have no overlap. Okay, they're orthogonal to one another. So all of these terms are going to be 0. All of them are going to be 0. And so what I get is Lx squared, Ly squared, Lz squared. Okay, so that's basically what I'm getting. I notice in the chat there's some discussion about a negative sign. Yes, there's a negative sign in front of the y component. Okay, that's always there. If you do a vector product, there's a negative sign, and I put the negative sign between the parentheses. So that's why some people were confused about why there isn't why the positions are the way they are. Okay, so this is now the magnitude of angular momentum squared. This is what it looks like. And what I'm going to do now is I'm going to make this into an operator. Okay, and I'm call it L squared. So L squared with a little hat is basically defined over here. Okay, so this is basically a definition that I'm having. I'm defining a new operator, and the operator is called L squared. It is the magnitude squared, okay, which is a different operator than the operator right here, which is Lz, that is the projection of angular momentum onto the z-axis. This guy is the overall magnitude of angular momentum, okay, squared. That's what it means. Now, why is this an important operator? Well, it is actually very relevant to kind of characterizing the angular motion of the particle, right? So I can actually write this thing out, because L squared is something that I have seen before. You may not have realized it, but in this formulation, this whole thing between brackets is what we call the Legendrian. Okay, this whole thing is called the Legendrian. It's basically the second order derivative with respect to space on the spherical surface. Right? The spherical surface only depends on theta and phi. Okay, and so I have second order derivatives with respect to both. This is the term. It looks really funny, but that's just because it's in angular coordinates. They always look a little funny compared to Cartesian coordinates. But this is the result. This Legendrian we have seen before when we derive these spherical harmonics. Okay, so basically the shape or the form of L squared, the operator, is minus h bar squared, and then the Legendrian, which is capital lambda squared. So that's what it looks like. So I have now two forms, right? I have two operators and two functional forms. Lz looks like this, and L squared looks like the expression right here at the bottom of the page. Okay, so why is that important? Why is this L squared important? Because L squared is basically momentum squared, angular momentum squared. And so that relates to energy, because energy is always momentum squared divided by 2m, or in the case of angular motion, 2I, where I is the moment of inertia. Okay, so here is my kinetic energy operator. Basically, the kinetic energy operator is angular momentum squared divided by 2I. I think we've seen this already before. Okay, and this is now the operator that I just derived a formula for. Now, this is the same as we did with the derivation of our spherical harmonics. Okay, this. And what we found is basically that that's the Legendrian. So this is the same expression as on the previous page, right? So what about the eigenvalues of this operator? Well, the eigenvalues of this operator, that means eigenvalues of the Legendrian, are of course the spherical harmonics. Okay, so the spherical harmonics are the eigenfunctions of the operator T with a little roof, little hat. Okay, so that's directly related to L squared. So if I know the eigenfunctions of T, I also know the eigenfunctions of L squared. All right. So, and of course, the way we computed it last time is through this equation. We solved this, we solved the eigenvalue equation of this operator, Legendrian, and then multiply it by this number right here. So the result was the spherical harmonics. Those were the eigenfunctions. And we can also write this as L comma ML, okay, and this kind of bracket notation. So this is the ket basically indicating a spherical harmonic function, which is now only indicated by L, whatever L is, and whatever ML is. That's enough. That's enough for me to make some important conclusions and statements about the situation I'm looking at. So remember that the Legendrian operating on L comma ML equals L plus 1. Okay, and then the function again. Right, so this is basically the eigenvalues of the Legendrian, which is given over here. So that relates directly to energy, as we have seen before. So let's put this together. If T is now operating on L comma ML, then I'm getting the following result. It's the eigenvalue is L plus 1, h bar squared, and then over 2I. Those are the eigenvalues for the kinetic energy operator. And this is the same as we have seen before. Okay, exactly the same as we have seen before. So that means that I also know something about the eigenvalues of L squared. L squared has as eigenvalues the following. It's L plus 1 times h bar squared, because the only difference between T and L squared is this factor 2I. So the 2I is taken out, and I'm just left with these eigenvalues. So that basically means that I have now the eigenvalues of this operator. I didn't really compute them. I just make use of the fact what I already know about angular momentum and about spherical harmonics. That's what we're doing right here. Okay, so the eigenvalues now I found them right here. Those are the eigenvalues of the angular momentum magnitude squared operator. Okay, and I already found this one. Okay, if LZ, the Z component of angular momentum, is operating on the spherical harmonics, L comma ML, then I found the following eigenfunction, that is the following eigenvalue, ML times h bar. That is the projection onto the z-axis. Okay, so angular momentum is a vector. The vector has always a magnitude, and a vector always has projections on each of the axes. And in this case, I can find the magnitude of angular momentum by looking at the operator L squared, and I can find the projection of this vector of angular momentum by looking at LZ, right? And I can have eigenvalues if the function is described by an eigenfunction like the spherical harmonics. Why is this important? Well, it's important because, of course, in quantum mechanics, these quantities can be quantized, right? If you have boundary conditions, that means that you can have quantization. That means that the eigenvalues are quantized, and they are, because look at L and ML, they are integers. So that means that the magnitude of this angular momentum is quantized. It can only have certain forms and certain numbers of the magnitude, and also its projections onto the z-axis are quantized. So the motion of a particle, of a quantum mechanical particle, on a sphere in terms of angular momentum are fully quantized, something we already know. Now here comes the new part, actually, and that's about the things that we can and that we cannot know. All right. So what we're going to do is we're going to ask ourselves the question: Can I say something about the x component of angular momentum and the y component of the angular momentum at the same time? Why is that? Because I would like to know if I can really precisely define what the angular momentum of the particle is. Okay, that basically means that I have a lot of information about what the particle is doing, how it's moving. It turns out, if you look at these two operators, Lx and Ly, these are both operators. I don't put the little hats there because it gets very clogged. Okay, so but these are operators, just to let you know. Lx and Ly are operators. You find that the commutation relation is not giving me a zero. In fact, it gives me I times h bar times Lz. What does that mean? That means if this is not zero, that means that these two guys don't share eigenfunctions. That means eigenfunctions of Lx are not eigenfunctions of Ly. And that means that if you know something about Lx, you cannot know something about Ly. Okay, this is an uncertainty relation. There's an uncertainty relation here between Lx and Ly. You cannot determine both Lx and Ly at the same time. That's what it says. So just like the uncertainty between space, x, and linear momentum, p, there was an uncertainty between them, the Heisenberg uncertainty principle. There's also a Heisenberg uncertainty principle between Lx and Ly. What about Ly and Lz? The same story, okay? It's also non-zero. Also non-zero. So you cannot simultaneously know the angular momentum projection along these two axes. And the same is true for Lz and Lx. Also, a non-zero quantity comes out. So if I summarize this whole thing, I have to say the following. We cannot simultaneously know all components of angular momentum. All right? So if I know what Lz is, then the first relation says basically that I cannot know something about x and y. Because you know Lz, that means you cannot know x and y. Another way to look at that is if you look at the second two, okay, if I know Lz, here's Lz, and here's Lz again, they do not commute with Ly or Lx. There's an uncertainty between them. And that means that once you know Lz very well, you don't know what Ly and Lx are. Okay? So there's an intrinsic uncertainty between the two, between the three, in fact. What about the magnitude? Is there an uncertainty between the magnitude of angular momentum and one of its projections, let's say Lx? So, in other words, can I know the overall magnitude, so how big is the angular momentum, and can I know something about the way in which it is projected onto the axis x in this case? And the answer is you can, because the commutation relation between the magnitude and one of its projections is zero. And the same is true, of course, for the projections along y and z. Okay, so this means, translation, that we can simultaneously know one component of angular momentum and the magnitude of angular momentum. Right? So the first commutation relations say, what you can do is you pick one, and we have picked Lz. Okay, Lz, we have chosen the z-axis as our reference axis because we know the projections. We know the z component according to this formalism. So the z component has very fixed numbers. We know exactly what they are. And if you know what they are, you cannot know the projections along x and y. That's what the uncertainty relation says. But if you know Lz, there it is, you can know simultaneously its projection and its magnitude. So both relations here can be simultaneously known. You just cannot know the projections along x and y, which means that these two relations don't make a lot of sense if you already know Lz, because Lx and Ly cannot be known. All right, so there's this uncertainty principle that we have learned about is much more broad than the application to x and p. to position and linear momentum. It also applies to angular momentum, and in a very interesting way. Okay, so this is a confusing picture, so let me walk you through it, all right? I'm considering here the following case. I consider a particle that can be characterized as having L equals 2. So the orbital angular momentum quantum number has the value 2, okay? So that is the quantum state of the particle. And if the particle has that quantum state, there's 5 options in total for the ML value that it can have, okay? So it can be -2, -1, 0, 1, and 2. Those are the possibilities. So let's say the particle happens to be in 2 and then -2. All right, so it can only have one set of quantum numbers. So let's choose, I'm going to say it's 2, -2. Okay, that is basically the state of my particle. I can write it as such, right? So I can write it in this kind of ket notation, like so. So the values are 2 for L, -2 for ML. So basically, that is going to be indicated in this picture right here. If it has ML equals -2, then my LZ is going to be ML H bar. That's going to be -2 H bar, right? And that's given over here. That's this value right here. So the projection along the Z-axis is this right here. Now, what does that mean? I mean, how do I kind of conceptualize that? How do I picture it in my mind? Well, do the following. We have here a sphere, okay? And you see here this axis. This axis is the axis that spins along. And so basically it moves, in this case, it moves in this direction. The particle moves in this direction on the sphere. You see the red arrow? It moves in this direction, like so. And that means it has an angular momentum that's pointing in this direction, right? So that's basically what these little pictures mean. So basically it says the motion is kind of like fixed in space. It moves in a certain way. It rotates in a certain way. If that is the case, this arrow here is basically the arrow L, okay? That is the angular momentum vector. So that is the way it spins. Now, what do I know about this L? Well, the formalism we just developed says you can know 2 things. One, you can know its projection onto the Z-axis. So I take this L, and I'm going to project it onto the Z-axis. That's what I'm doing right here. And its projection is going to be -2 H bar. So if you project the angular momentum vector onto the Z-axis, which we have chosen as our reference axis, then I can conclude that its projection of the angular momentum, when it spins in this way, as indicated here, is going to be -2 H bar. I can also know something about the magnitude of this arrow, of this vector, because the magnitude is something I can know, right? I can know that because the magnitude of angular momentum is L squared. I take the square root of that. So basically, the eigenvalues for the L square operator were L plus 1, H bar squared. If I take the square root of that, this is the result. Right? So this is the magnitude of angular momentum. So I can know the magnitude of this arrow. That's basically what I can know. So basically, if I look at this arrow right here, that is the overall magnitude of L. That is L. So that is the magnitude of L, right? And the projection of L onto this axis is right here. So it has a magnitude. The magnitude in this case, when L equals 2, is 2. And 2 plus 1 is 3. 2 times 3 is 6. So square root of 6 H bar is the length of this arrow right here. And the projection onto the Z-axis is going to be -2 H bar. And what does this kind of like strange cone mean? Well, that means the following. Because we have chosen LZ, so the Z-axis, as our reference axis, we don't know anything about Lx and Ly. We don't know the components, the projections onto X and Y. So Ly and Lx, we don't know. We don't know anything about it. So that means the XY plane is unknown. That means we just draw a circle. We can only say that this vector L has a certain length. It spins around, okay? It's uncertain where it is located along X and Y. That means it kind of carves out this cone. I know it must be somewhere on the cone, but I cannot say where because I don't know what Lx and Ly are. I don't know those components. That's unknown. And that's what these cones mean. They basically indicate the uncertainty of the problem, right? So the projections along LZ are known, and the magnitude is known, but the projections along Y and X are not known, and that's why I have these cones. And the same is true for the different values for ML. I just started with -2, but -1 is the next one, okay? That is the next one. That's this example right here. In that case, I have the particle spinning this way. So it spins again in the same way, but the whole sphere is rotated a little bit, as you can see. The overall L is now tilted, and that means that its projection onto the z-axis is less. It's going to be -h. This is a situation when a particle is spinning like so, right? And now L is directed basically in the xy plane. It is a circle here because we don't know where in the xy plane it sits. We only know that it is in the xy plane. So that's the fundamental uncertainty. And the same here for these rotations. So the things that I can know about this problem is that, yes, if the particle is allowed to move, as quantum mechanical particles moving on the sphere, it is fixed in space. If I choose a reference axis, I can know its projections along the axis, along that axis, but I cannot know the other two axes. That's what these cones mean. So that's the uncertainty about the angular momentum of the problem. Okay, now this is what we just looked at. ML is running from -L to +L in integer steps. That's how L and ML are related. And for orbital angular momentum, we call the overall orbital angular momentum L and its projections ML. This is also called the magnetic moment due to angular momentum. Now we know that these L and ML have values because L, the orbital angular momentum quantum number, must be an integer. Okay, this is something we have already noticed. Okay, and that there are two L + 1 values of ML. However, I can make this more general. I can say, well, if I have anything that has to do with angular momentum, not necessarily orbital angular momentum. Orbital angular momentum means a particle that is spinning in an orbit, okay, let's say on a sphere. That's the most intuitive picture that you can have about angular momentum. But I can make this more general. I can say, I can call anything that has angular momentum the quantum number J. So I'm going to make it more general. The L I'm going to call J, and J is a general angular momentum quantum number. But the relation with Mj is the same as the one between L and ML. Okay, it basically, Mj runs from -J to +J. So all I do is just replace L with J, and the statement I'm making is that J is more general than L. L is only orbital angular momentum, and J can be any type of angular momentum. You ask yourself, what other types of angular momentum are there? And I'll show you one, very important one, in about 2 or 3 minutes. Okay, of course, I have two J + 1 values of Mj. That is the same. It's just the same relation above. I just replace L with J with the stipulation that J supposedly is more general than L. Okay, but the relations are, of course, the same. J squared, that is the L squared operator now, called J, has the following relation. That is exactly the same thing as I saw before. The magnitude squared has these eigenvalues, J + 1, h bar squared. And the eigenstates of J are indicated by J, Mj. Are these the spherical harmonics? Well, they are if we're dealing with orbital angular momentum. But in the general case, we don't really know what the function looks like. We only know that it's labeled by a J and an Mj. And that turns out to be sufficient for most problems. We don't need to know the functional forms. We just need to know how these eigenstates are related to their operators. The projection operator is now called Jz, and of course it has values Mj, h bar. It's exactly the same as before. So what does that mean? That means this set of relations, these 3 lines here, define, quantum mechanically speaking, what angular momentum is. This is angular momentum. If you have an operator that has the following properties, then that operator is an angular momentum operator. Doesn't matter what I call J, you can call it L or S or B or C, doesn't matter. If it has these relations with its eigenfunctions, then that operator has the characteristics of angular momentum. Now, why do I say it in that way? It sounds very cryptic. That's because there is a very important other form of angular momentum that we all know about, but you may not have realized. And that is spin angular momentum. Spin, the electron spin, is a form of angular momentum. Okay, so what does that mean? Let's call this thing not J, but S. Okay, so S is the orbital angular, not the orbital, the spin angular momentum quantum number. Look at the number, it's not an integer, but that was not a stipulation here. Okay, that was not a necessity. I didn't require that J needs to have integer values. It just said this is a set of relations. That's all. Okay, so if I take J and I call it S, and I say J has a value half, clearly that's not an integer. But if I do that, then I can define the following values for MS, namely minus half plus half. Why? Because I have two values for MS. 2 times S, when S is half, so that's 1, plus 1, 2 values of MS, right? And the values are minus half plus half, because MS is running from negative S to positive S in integer steps, just as the situation above, all right? So only one quantum number for S, that's it. There are no other quantum numbers. In orbital angular momentum, this L was an integer that could run from 0 to infinity, right? Here, this S has only one value. So in a way, this is the simplest possible angular momentum that you can have, where the angular momentum quantum number only has one value, namely half. And that means it only has 2 projections. MS equals minus half and plus half. Now, what are the eigenstates of this particular case? Now, the general eigenstates are always called J, Mj, and this J is now called S. So the eigenstates are S, Ms. Now, what are these then? Well, they're the following. I can call one alpha, where S is half and Ms is plus half, and the other one I can call beta, where S is again half, because that's the only possible number for S, but Ms can have another value that's half, the negative sign. Okay, so alpha and beta are the 2 spin states. Are there more states? No. These are the only possibilities, because S can only have one value. There are only 2 projections, and therefore there are only 2 states. These are the 2 possible spin states for the electron. Okay, we can do 2 more things. And that is, once we know the states, and we have them right here, one is here, one is there, I can operate on these states with the magnitude operator and the projection operator. The magnitude operator is now called S squared, and the projection operator is called SZ. So let's do that. S squared operating on alpha is going to be, look at the situation above, J plus 1, H bar. The J is now an S. S plus 1, H bar. Okay, S, of course, is half. That's the quantum number. And that means the answer is going to be 3/4 H bar squared times alpha. So the eigenvalue is the following. This is the square magnitude of the spin of the electron if it is in state alpha. If it is in state beta, it's exactly the same, because the magnitude doesn't change, only the projection has changed between alpha and beta. So in both cases, in both spin states of the electron, the angular momentum due to its spin is the same. And the magnitude is given right here. The magnitude of an electron, the angular momentum of an electron due to its spin, is 3/4 times H bar squared. That's it, always. And the projections are SZ operating on alpha is going to give me the projection. It's always Mj times H bar, where J is now S, so I get Ms H bar and ms in this case is half, okay, for alpha. So I get half h bar. That is the magnitude projected onto the z-axis for the electron when it is in state alpha. When it is in state beta, it's going to be the negative of that. Okay, so the magnitude of its projection is negative half h bar. So here we can see that the electron has, besides orbital angular momentum, another form of angular momentum. It's called spin angular momentum. The spin, like the orbital angular momentum, has a magnitude and it has a projection. We choose the z-axis as our reference axis, and that means that it has projections that can have only two values, half h bar and negative half h bar, depending on whether the state of the electron is alpha or beta. Okay, so the formalism of angular momentum is actually extraordinarily powerful. This may sound very abstract and unfamiliar to you, but it turns out this angular momentum framework is really powerful to explain a lot of properties of electrons when they're part of an atom. This is why we are going through this. But for us, the take-home message is really this point that we ended on, which is that spin angular momentum is yet another source of angular momentum that follows the same rules as that of orbital angular momentum, except for the fact that the quantum number s is half and only has one value, whereas L is an integer running from 0 to infinity. Okay, that is the only difference from a quantum mechanical point of view. Okay, that's it, folks. Any questions about this? Yeah, spin. The spin I'm talking about here is electron spin. Okay, but there is more. I mean, spin in quantum mechanics can also be applied to other particles, like a proton or a neutron or an entire nucleus, right? And so you know that nuclei also have spin, and that's the same kind of spin as the spin we're talking about right here, except for the fact that the spin can have a different value. So there's integer spins, there's half integer spins, and there's also spins that have values of 3/2 and so forth. Okay, so nuclear spins are pretty much the same thing as the electron spin. The nice thing about electron spin is that the S value is always half. And in the case of a nuclear spin, the value can have, the number can be different. But the formalism is exactly the same. So it's a very general formalism for all particles that have quantum mechanical character.
Does the z component, does the component only works with the z-axis, or does it also work with the x and y-axis too?
It works in exactly the same way with the x and y axes if you choose your reference axis to be x or y. And if I choose x as my reference axis, then consequently I cannot know anything about z and y. And then my operator, my projection operator, is not called sz, but it's called sx, right? So you have to make a choice. Quantum mechanics says you have to make a choice. You choose one reference axis and then you work with that. And that means you lose all information about the other two axes. So which one do we choose? Well, it's pretty arbitrary. We choose z, okay? But it's z in Cartesian coordinates. It's very arbitrary. We just have one axis and we say, well, that's one direction I'm choosing and everything is going to be a reference to it. That's all. So it doesn't matter which one you choose. It's arbitrary. But again, once you choose it, you know for sure that you don't know the information about the other two directions. You can only know that direction that you make an initial reference with.
Will it affect the picture you showed us earlier, or will it take how it opens up on the z-axis?
Well, I mean, if you go to this page right here, this page, I said this is z, right? The top is z. So I say z is my reference axis. That means I'll lose information about y and x. The components along y and x are ill-defined. If I rotate this whole thing around so that all these cones are now aligned along x, then I know everything about x, but I don't know things about LZ and LY. So this picture remains exactly the same, but this picture can rotate depending on which axis you choose, okay? So the picture is internally consistent. It's always the same. The picture is always the same. It's just that, you know, our uncertainty about which axis to choose makes this picture rotate along one of the axes. That's all. I mean, you can also say the following, right? So in the Heisenberg uncertainty principle, if you know something about X a lot, you don't know something about P. That's the uncertainty. And vice versa. If you choose to know something about P, you don't know a lot about X. So the question is, what do you choose, X or P? Well, that's up to you. You know, you have to make a decision. You cannot say, well, I don't know. Okay, you have to make a decision. So I say, well, I choose to be you know, very cognizant of what X is. And that means you lose a lot of information about P. And it's the same here. I'm choosing to know things about the projection along the Z-axis. So, well, if you do that, then you know you don't know the answer about the projections along X and Y. So that's how you should think about it. You know, it's basically it's our knowledge of the situation that is compromised, right? The quantum mechanically everything is fine. It's just like if we ask questions of the system, we have to make a decision. Do you want to know this or that? You just cannot know it at the same time. So we choose one axis, Z is perfectly fine, and we give up on X and Y. Since it's arbitrary, it doesn't matter what we choose. So Z is convenient to work with, and it's easy to conceptualize, I think. That's why the framework is the way it's being presented in textbooks and so forth.